Alright, so this should be working now again. So in the last session we went over chapter 13.1 and 2, primarily focusing on functions of two or more variables, as well as trying to find the limits of these different equations with these two or more variables. We also looked at contour maps, which is really cool. Level curves, which we can find by intersecting a quadric surface with a plane of some height k. In this case, we use the plane z equals 2. When we plug that in, we get that graph there, y equals 1/2 x squared, which can be used to create a two-dimensional representation of a three-dimensional graph or whatever. So that's interesting. Now we're going to continue on with chapter 13.3. So we're going to be looking at partial derivatives. Now, I'm familiar with regular derivatives. I don't know what it means to get a partial derivative, but I guess that's kind of what we're here for, right? So it's not 3. But yeah, partial derivatives, right? Let's see. Now we will discuss the derivatives of functions of two or more variables. In two-space, when we take a derivative, we always do so with respect to the independent variable. So for example, if y equals f of x, then dy over dx would be equal to f prime of x, since we take the derivative of y with respect to x. If, again, for example, we have s is equal to s of t, the derivative would then be ds over dt, which would be also equal to s prime of t. Again, derivative of s with respect to t, in this case time. Of course, it gets a little complicated now that we have more dimensions. Now there are two independent variables. So in the case of, for example, we have some z, right, equal to the input that's taking in both x and y. Right, how do we derive this? So do we take the derivative with respect to x or y? If we take the derivative with respect to x, what happens to y? These are all reasonable questions. I don't know, which is why we're here. So, introduce a new concept, partial derivatives. We will take the derivative with respect to x and hold y constant, or we will take the derivative with respect to y and hold x constant. So one or the other one stays a constant, right? When we hold one of the independent variables constant and take the derivative in terms of the other, we call this a partial derivative, and we use a new symbol. I'm just going to say d over dx or d over dy. Just as there are first derivatives, there are first order partials. So, okay, so this is a first order partial derivatives, right? Right, and in this case we have some z equal to now 3x squared y squared plus 8x. Right, we see that this y is taking in both x, this z, is taking in both that x and that y, right? Hold on, I have like no music playing in my headphones and I kind of want it. I've been on like this like Japanese funk jazz kind of like thingamabobble. Or really just jazz in general. Like Cortex is really good. You guys should listen to them. Chople Bleu. This is a really good album. Sorry, I just went on a tangent. I kind of just want to play this and then continue on forth with the lesson. See, that's like playing out loud. Hold on. Apologies, folks. I think I paused this too. I didn't. Okay, great. You know, I don't know what it is. I can't listen to music like to study, but you know, having like a nice like non-lyrical album is actually really good. So I do really like that. Except I guess this album just doesn't fucking exist on YouTube or something. I don't know what's going on here. But it's really good. Yeah, I don't know. I'll just play the same playlist I played last time. I don't really know. It's taking way longer than I thought it would. Whatever. Alright. Anyway, here we're gonna continue with this. Yeah, z is equal to 3x squared, y squared plus 8x. How do we find the first order partial for this, right? So first you do it with respect to x. So in this case, we'll consider any y value a constant in the first term. 3y cubed. What's 3y cubed? 3y cubed will be a constant coefficient and thus will be unaffected by the derivative. Okay, so we'll do with respect to x. So here we have the partial derivative of z with respect to x is equal to now 3y cubed times that 2x, because we're taking this y cubed, or this 3y cubed, as a constant, right? We're removing this kind of from the x squared, and then we're differentiating that x squared. And here we get 2x plus, of course, 8, because the derivative of 8x is just 8, right? Simplifying, we get that 6x y cubed plus 8 is the first order partial with respect to x. That's good. And now we would do it with respect to y, right? So in this case, the x term would be constant. So the partial of z with respect to x, or y rather, would then be equal to that 3x squared, which now gets removed because it's a constant, times huh? Am I an idiot? I'm confused. I get that 8x would become 0. That 3x squared would be pulled out, right? So would we not? I'm confused. Because, for example, when we did z, right, with respect to x, I get the fact that you kind of took off that 3y cubed, right, because that's a constant, multiplied now by x squared plus 8. That x squared would be differentiated, it'd become 2x, and then plus 8 because that x goes away, right? With respect to y, though, I get the 3x squared, that becomes a constant, right? And then you differentiate 3y cubed, or not 3y cubed, but y cubed, and you get 3y squared. I think she messed up on that. Yeah, that'd be 3y squared plus now 0, because that entire 8x would become a constant, and therefore becoming 0. So we would then get 3 times 3, so 9x squared y squared is going to be equal to that partial. Right? So this would be the, which I guess it kind of makes sense why it's called a partial derivative now, because we're literally just taking partials of the original function. So I guess that makes sense. Not too bad. In this case, we have a rather long one. So here we have where z is equal to now x squared times the natural log of xy. Let's find the derivative with respect to x first. In this case, this would be a product rule. So we would do 2x times now that ln of xy plus that x squared times the derivative of ln is just 1 over x, so it'd be 1 over xy, right, times now the derivative of xy, which would just be y. So your total thing would be that 2x ln of xy now multiplied by this y would cancel, this x would cancel, so this would just be plus x. Yeah, is that right? Yeah, it is. Okay, perfect. So this would be the partial now of z with respect to that x. Really not that bad. I'm assuming it's going to get a lot more difficult later on, but here, let's do a partial of z now with respect to the y. In this case, I'm just going to read off because I can't be asked to do it. Then becomes that. So this x squared would stay here because it's a constant. Times now 1 over yx, or xy rather, sorry, xy, times now x, because that y would go away, which would now just be equal to x squared over y. And this would be your partial with respect to the z-axis. These fucking partials are pissing me off. I don't like drawing them at all. So this is x squared over y. I think you just leave it like that now. Why was the partial with respect to x more complicated? Because x was a variable and we have two factors within x. This product rule and then in the term chain rule, the x squared proof is constant, so the product rule is needed. Right. Nothing too crazy. Now is where we get a bit iffy because we're going to look at the representation. So what exactly does that mean? I know, right? I know with the derivative in like a, what's it called? Like a two-dimensional space, for example, like on a regular XY axis. I know that taking the derivative, right, will give you that slope at that specific point. It'll give you an equation. For example, you're taking the derivative of y equals 2x, right? You know, the slope is constant, so taking the derivative of that would give you an equation for the slope. Now, with the first order partial derivative, it's a little interesting, so let's go. When we take partials, we are indeed getting two different answers. It would give us two different equations for slope, I'm assuming. Yeah, the slope of the tangent to the curve in two space. The partial derivative also represents the slope of the tangent to a curve, but it is a little more complicated. Here we can see we have an x, y, and z plane. Right, we have some sheet. What the fuck am I looking at right now? I hate when they do that. We will go over this in class. Okay, what if I wasn't there? Am I just cooked? Like, I don't understand what you want me to do. But essentially what is happening in the first drawing is that the orange surface represents the function z equals f of x and y, and the blue plane is equal to y equals y prime, which means y is a constant value. the plane and the surface intersect at curve C. What you find when you find the partial of z with respect to x, you are determining the slope of the tangent to the curve C1. Okay, and the second drawing, the blue plane is x equals x naught. So x is constant, and the new curve of intersection is formed C2. When we take the partial with respect to y, we are finding the slope of the tangent to this new curve. We are finding slopes to two different curves, which is why the first order partials are different. Okay, so for example, in this one, right, that y naught is going to be constant. And if you remember, when we take the partial with respect to x, that y becomes constant. Therefore, we're creating this curve, right? And this curve, because that plane and that surface intersect at that point, at that little that intersection, that curve C1. So when we find the partial with respect to x, we are determining the slope of that tangent to that curve, C1. Same thing with this one. You can tell because that x naught is going to be constant, which means we're taking the partial with respect to y. And you get two different ones, so yeah. So partials represents slopes of tangents, but just like derivatives in two space. This is a beefy example. Let me just prepare my health myself. Okay. Let's try this one. In this case, it's saying to find the slope of the tangent to the curve formed by the intersection of the surface. So for example, it's giving us some z is equal to 2xy minus e to the x plus 4y squared. The plane y is equal to 2, where y is constant. At the point 0, 0, 2, 15. Okay, so it's saying to find the slope of the tangent to the curve. So, okay. I believe in the dream. I'm trying not to look at the blue, but I already looked at it. So the slope will be the partial with respect to x. I understood that because if you can see just by the keywords, y is constant, which means that that x would be treated as a variable. So we would have to find the partial of z with respect to x, right? And in this case, it's actually pretty easy because we just get 2y minus e to the x plus 0. Therefore, by square goes. And then here we're going to be evaluating, right, at that 0, 2. Because it's literally giving us the point that we have to find it at. So when we plug this in, we get 2 times 2 minus e to the naught. So that'd just be 3. So that 3 would be the slope of that tangent. I'm convinced that 15 is just there for no reason then. That's not too bad. Let's see. This is just rate of change. So, for example, the lateral surface of a can is given by the formula x is equal to this. Can be 2 pi r times h plus 2 pi r squared. If the base remains a constant value of 4 inches, but the radius varies, what is the rate of change of the surface area when r is equal to 2 inches? So, I think this is like implicit differentiation, no? Or I don't know. Let's see. R is equal to 2 and h is equal to 4, right? We're given 2 initial values to begin with. Find the partial of this now, because we know that the height is going to be constant, right? We know that right off the bat. Now it's saying, it's saying the height is constant, the radius varies, right? We're trying to find out what the rate of change of the surface area is when r is equal to 2 inches. In this case, when we find that partial, right, that 2 pi, that h is a constant, so this would be 2 pi h, right, plus now 4 pi r. And in this case, when we plug in all of our values, we just get that 2 pi times 4 plus 4 pi times 2. We get is equal to 16 pi. In this case, I'm just squared. Seems like this one doesn't use implicit differentiation. I'm assuming that. I'm pretty sure in like Calc 1 that would be implicit. It's a little interesting. But yeah. Okay. Now we're going to be looking at higher order partials. Right, okay. So just like we have higher order derivatives, we have higher order partials, which let's first discuss new terminology. In two-space, we use prime notation to represent derivatives. For partials, we use subscript notation. Okay, so for example, if we were to do the partial of z over x, right, with respect to x, it would be equal to f of x times x comma y. And then if you were to take the partial of z, right, with respect to that y, it would now be f of y, x comma y. Okay, so let's first investigate second order partials. In two-space, there's only one second derivative, and we find by taking the derivative of the first derivative. Again, in three-space, it gets a little more complicated. So we have 2 first order partials, and we can take the partial of each one with respect to both x and y, so that gives us a total of 4 second order partials. Holy shit. Okay. So for example here, we have that z is going to be equal to 5x cubed y to the 5th, right? So in this case, the partial with respect to x, in this case, would be something pretty simple. It'd just be 15x squared y to the 5th, because that y and that 5 are going to be constant. Just dropping that over. The partial now with respect to y is going to be equal to 25x cubed y to the 4th, right? We will now take the partial of with respect to x, and then with respect to y. So, okay, what the fuck? So, the second partial of z with respect to x, right? Here we know that x again becomes the, so it'd be 30 y to the 5th x. And now the partial of z with respect to y and z. And y, I mean. And what the fuck am I saying? An x. That's a little interesting. That's strange. I think that was a mistake. Yeah, I think this was a mistake. I think it should just be dy, no? And then it would be 75, right? X squared. X cubed, I mean. Wait, what? Oh, I'm an idiot. Sorry, I'm an idiot. So this now becomes our point of reference. Sorry, my brain is tweaking. So we go from here to here, right? And now we do it the partial of z, right, with respect to y and then x. We get from this. So in this case, we would do that that y, which would give us 75 x to the 2nd, y to the 4th. And then now what we do is we now take this one, which would be the partial respect to x now would be 75 x squared y to the 4th, right? And then we would get the second order partial of z with respect to y would be equal to that 100x cubed y cubed. So here we get kind of these two separate, in total four different equations. My brain was like totally fried for that, I'm not even gonna lie to you. Anyway, yeah, it's interesting. So essentially we found the derivative with respect to x, and then we differentiate it again with y to be that well, no, we take it with respect to x and then we take it with respect to y. In this case, we take it with respect to x. That y would be the constant, and then now we take the second derivative, the second order partial with respect to y. In this case, that 15y to the 5th, the 15x squared would become a constant, right? And then that y to the 5th, that 5 would drop down. 5 times 15, 75, 75. And then that y to the 5th minus 1 would be y to the 4th, I mean, right? And then now we take the other equation, the partial with respect to y, and then we take that with respect to x, and then we take that one again with respect to y, and then here we get our total of 4 equations. Did I notice anything interesting about the second order partials? Wow, there is absolutely more. Okay, let's take the third order partials. There will be 8 of them. Y, we will take a partial with respect to x and y of each second order partial. So it would be, for example, 2 for this one, 2 for this one, 2 for this one, 2 for this one. So 2 times 2, it'd be 2 times 1, 2 times 4, which would be 8. When we do that, we get a bunch of different values. And in this case, some of the third order partials are actually equal. So you have 30xy 5th, 30y 5th, 100y x 4th, 150y x 4th. We see that 75x squared y 4th. We see the 150x y 4th. 3 times actually, so that's pretty weird. So now you can see that some of the third order partials are equal. Which ones? Notice the order does not matter, but the number of x and y's does. For example, all the ones in red have 1 x and 2 y's. And all the blues have 2 x's and 1 y. This is called the equality of mixed partials. So that's interesting. There's like this pattern that exists, which is pretty cool. The subscript can be cumbersome, so we usually use the subscript notation for higher orders. We do the partials from right to left for the notation, but the opposite for subscript. So if you want to take the partial with respect to x first and then take the partial with respect to y, the two notation would be written as, okay, so for this one, for example, we took the partial with respect to x, so that would go to the second one. We're going from right to left, kind of, and then with respect to y, but if we do it in this notation, it would be that way. So if we wanted to find the third order partial by taking the partial with respect to x, that would go all the way on the right. That would be the partial y and then partial x squared, and then it'd be different for the f because you're taking x and then y. Wow, okay, that's a lot of work. So given f of x comma y of x cosine 2y, determine f y y x y of 3 comma pi. First find the fourth order partial and then evaluate at the given point. So we find f x y, that's just x cosine 2y. Taking it with respect to y, that x would be a constant, so we'd get negative 2x sine 2y. Sorry guys, I'm like insanely tired. I'm gonna record again after this, and instead I'm gonna go over the VR gaming project that I kind of showed off the last time I was here, or the first time. But yeah, some progress had been made, not a lot. So hopefully this will keep me accountable. But yeah, whatever. Back to this. Anyway, now we're taking fyy. So we're taking this with respect to y again. So a partial of z over partial of y squared. And then we're taking that with respect to x, and then we're taking that with respect to y. So we're finding this kind of like a specific like pattern here. And then given this, then you just evaluate, and then you get this specifically. So honestly, really not that difficult. Really only like 2 pages of notes. We'll go over this though. So in this case, taking partial derivatives in 3 space, right? We're gonna have to set one of the variables to constant. So for example, if we were to take this equation, for example, if you want to find the derivative, the partial, you would have to take the partial derivative, right? Because there's 2 kind of independent variables here. So we set one of those to be a constant. In this case, it would be x, so you're taking it with respect to y. And really what this essentially means is, like on a representation, since you're holding, like for example, if in this case, that y is constant, so this is with respect to that x, you're kind of forming this curve, and then evaluating that at a single point, you'll be able to find the slope of this curve, right, at that point. Same thing for this one. In this case, you're taking it with respect to y because that x is going to be constant, creating this plane, thus creating this curve. Jesus Christ. And then at a single point, you'll be able to find that tangent to that specific curve that you're actually making. What the fuck is that? That's scary. Anyway, yeah, kind of like what you're doing here, right? The plane y equals 2, y is constant. So you're taking it with respect to x at this specific point, 0, 2, 15. That tangent that you're creating based off of that plane, that curve that you're creating, you're finding the tangent at that specific point, which in this case would be positive 3, right? And this would also represent rates of change. So given some equation that would give you the surface area, right, in 3 space, because you have a height and you have a radius, right? You have 2 independent variables. In this case, it's telling us that the height is going to be a constant value of 4, so you can set the h equal to that constant value, but the radius is going to vary. Thus, you're taking the partial of the surface area with respect to that radius. thus holding everything else constant, but only differentiating that specific r. So in this case, you get this. You evaluate that at r equals 2 and h is equal to 4 to get the rate of change, right? When at that point. Higher order. This is where it gets just a little funky. Realistically, here, we start with this original function, right? We take the first two first order partials of x and y, and then afterwards you take the partial of both of these. So for the first one, you take the partial with respect to x and then respect with y. With that y, the partial with respect to y, you take it with respect to x and then y again, thus leaving you with a total of yeah, you get two first order partials, and then it kind of doubles, and then you get 4 second order partials, and then when you go again to third order, you would get 8, because every single one of these are going to get differentiated. So that 30x y fifth, that 75x squared y fourth, that 75x squared y fourth, and notice how these have the xy. The ones that are the same usually end off with the same ones, which I find really interesting. Like that 150, that 150, that 150, they all end off with that xyx, yx squared, or x squared y. While they might be in different orders, realistically is the same exact thing. And this is basically showing the equality of mixed partials, because the number of x's and y's is what necessarily matters when it comes to equating them, not really the order. And here's just some syntax. And yeah, really not that difficult. Honestly, I thought it'd be way harder, but that's partial derivatives. Honestly, could very well be more difficult. I'm gonna cut this off right now before I literally faint because I'm extremely tired. I'll be back though. I'll probably take a Celsius and then record the VR thing. It's gonna be interesting. The next time I approach calculus will probably be tomorrow. We're going to be going over the homework for the last topic, 13.1, 13.2, and then now 13.3. Sorry for the noise. But yeah, thank you guys, ladies, gadies, and gentlemen. I'll see you guys. Thank you very much.